Hello everyone. Uh, let's wait for a couple of minutes so that uh, the rest of you can join the session. Hello everyone. I guess we should start the session since it's already 3:02. So this is our third session, and you are currently learning the course by Professor Sanjeev Sambavan on NPTEL, and we try to solve the problems in this kind of sessions which are being held weekly and is not audible. Now is it fine? Hello. Better. So it can be. Wait a second. Full screen mode. Okay. You can do one thing. You can. I can do that, but uh, it might cause me some issues while doing this. I can do that, but while people are joining as well, noise is in the background. Stupid this thing. Now is it fine? Hello. Okay. Uh, Regarding that full screen mode, I will not be able to admit the people to the meeting. So I request you to pin this screen that I am sharing so that you can concentrate on that screen only, and rest of the things won't disturb you then. So if it's audible now, let's start with this problem regarding this body-centered cubic lattice. In the previous session, when we finished when we were finishing the last problem, we saw that this silicon basically consists of two interpenetrating FCCs, and with one FCC, if we consider one FCC at the let's say its one point is at the origin 000, then the corresponding point of the another FCC will lie at a distance of quarter 1 by 4th from this 00 point in all the three directions. That is, it will be 1 by 4 in the x, 1 by 4 in the y, and 1 by 4 in the z. So that was all about that FCC, interpenetrating FCC or diamond lattice that we called on that day. So today, basically, this is a simpler version of of the problem. In here, this we have been told to uh, find the lattice points which are lying in the body centered cubic cell, but we have to look it in terms of a unit cell. So how many lattice points are there in a particular unit cell of the body centered cubic? So you all must be knowing that this body centered cubic, sorry, this body centered cubic, if I draw it like this, some cube, so it will be having these atoms, 8 atoms at the corners. My drawing might not be that good, so these corners will be having 8 corners will be having 8 atoms, which will be shared between the rest of the 8, and we will be having one atom lying in the middle of the body. We can say in the middle of the body, if we consider this as the body, and this along this diagonal, which is the body diagonal, we will be having one atom lying just at the center of this body diagonal. So as we all know that this kind of cubic lattice will be having only 2 atoms per unit cell, because the 8 atoms will be shared with the rest of the 8 and one atom will be lying inside the body. So the answer to this problem is simply 2. Now moving towards another problem. When we studied that what we can say, that silicon lattice, that FCC, to interpenetrating FCC lattice, and we said in that particular lecture, wait a second, we said that in that particular lecture that these this kind of lattice is known as to be the what we can say as the diamond lattice, because the two basis atoms were of the same kind. Now in here, this gallium arsenide, since these are two different kind of atoms, one is gallium and other is the arsenine, and these kind of atoms, when they form a basis, they are known by the name of zinc blende. Okay, so which is I have mentioned it there in the problem as well, that which is equivalent to face centered cubic with two atoms per lattice point. So it makes it 2 atoms per lattice point. So one will be of the gallium and another will be of the arsenic. So we have been told, we did one problem which was in that particular FCC kind of a thing for silicon, that we were required to find this atomic densities as well as the we can say the number of atoms per unit volume. We saw that in that particular problem. Now in this case, we are having two different atoms which are forming a zinc blende crystal structure. And now in here, let us try to solve this by writing these things explicitly, so that we don't get confused with this diamond lattice and zinc blende structure. So the first thing here is that we have two atoms per lattice point. This is the first point. Now we know that face-centered cubic cell. It is we have seen it in the previous class as well, that this face-centered cubic cell will be having 4 atoms per unit cell, one lying at the corner which is being shared between the rest of the 8, and rest we will be having 3 atoms like lying on different 6 atoms lying on different faces which are being shared with the other, and as a result of which we will be having total 4 atoms. So this FCC has 4 lattice points per unit cell. Now, now we have 2 atoms at a 1 lattice point, and FCC has 4 lattice points. So it means that this number of atoms, this number of atoms in this gallium arsenide will simply be number of gallium arsenide atoms per unit cell will simply be 4 multiplied by 2, and it will be 8. That's what we found in the silicon as well, but in that kind of a problem they were all of the same kind. They were all silicon atoms, but in here we will be having one gallium atom and one arsenic atom. For example, if this gallium atom is lying at we can say 000 coordinate in the some plane, and in another this other atom, this arsenine, will be lying at 1 by 4th, 1 by 4th, and 1 by 4th from this gallium atom. So basically we are having the same silicon structure, but only the only difference here is that this one silicon atom will be replaced by the gallium, and the another silicon atom will be replaced by the arsenic. Now this problem says that we have to find the number of atoms per cubic volume in this. So this simply means that we have to look at the lattice constant first. Since this is a cubic structure, we will be looking at the volume. Since A is given to be equal to 5 point, it is here 5.65 angstroms, it means that volume is simply AQ, which is 5.65 into 10 to the power of minus 8 cube centimeter cube. Okay, since it is given in the CC, that's why I am doing it in cubic centimeter. Okay, now okay, now the number of atoms is 8, and therefore this number of atoms per cubic centimeter will simply be number of atoms divided by AQ, which is simply 8 divided by, which was this value 5.65 into 10 to the power of minus 8. Let me calculate it. 5.65 raised power 3, it is 180.36 into 10 to the power of minus 24, so it will be 10 to the power of 24 above, and let's divide this 8 with this thing, 0.36, so it will be 4.4 35 something something into 10 to the power of 22 per cubic centimeter. So this is the number of atoms per cubic volume for this gallium arsenide, and it comes out to be equal to option B. So the option B is the correct option. Now let's move to another problem, which says that uh, uh, this EK relation that you all must have gone through by now in the lectures, that how this Croning Penny model helps us to get a brief idea about these things, how this band gap evolves, and how we can manipulate these things to get information regarding a particular material. So in here, this EK relation, this EK relation uh, almost contains I shouldn't say almost, it contains the information that we will be needing for studying any material. So this EK relation over here, has to be found, that this mean time, we have to find this mean free time for these electrons in the conduction band by this kind of a relation, by using this EK relation. So uh, as we know that this there is some relation between the mobility and the mean free time. We can use that relation, and after using that relation, uh, we can get the value for this mean free time. So can anyone among you tell me what is this mean free time? So, let it be wrong, no problem. Tanish,
एवरेज नंबर ऑफ इलेक्ट्रॉन्स
then
कोलिशन से पहले
what can you mean by this term, this mean free time of electrons?
कोलिशन से पहले का टाइम जो होता है
हाँ, हम कह सकते हैं, हाँ. If any other?
Tau?
हाँ, hello.
Yeah, tau. That is effective mass by um,
No, I don't want any relationship. You can just say what does this mean? This mean free time.
the
Okay. Uh, Neeraj.
Yes, yes. Hello.
Okay. Can you comment on this?
It is, I think, the average time.
Okay, for what?
Uh, Average time between the electrons.
to move from conduction band to valence band.
Any other? Uh,
Mean
Shri,
free time is the average time between the collisions.
yes. You can say. So this is you people can mute. Neeraj, you can mute yourself. So, oh, thank you. So as all of you rightly said, that this is some mean time. We are saying it as a mean time because one electron may collide with another electron. Hypothetically, let's not consider these as the times that I will be telling over here. Let's consider these as hypothetical times. They may not be strictly correct. Let's say that they collide with each other. One electron collides with another electron in let's say 10 nanoseconds. and while other collides with the same electron in 1 nanosecond. So overall, we are taking the mean of those all the collisions. These mean how much for how much time that these electrons collided with a particular electron, and this collision time will roughly give us the estimate that how frequent the collisions are happening, because the more frequency in these collisions, the less will be the mobility. This will result in the degradation to the mobility. So as all of you rightly said, that it is some kind of an average time between the two collisions that are happening between the electrons. In this case, it is in the conduction band. These can happen in the valence band as well for the holes. The collisions in the between the holes will enable us to calculate the hole mobility. Basically, if we see it, it will follow some random kind of path that is known by the name of a random walk. If we try to solve this, that how this thing happens, it will be kind of a probabilistic in nature. It won't be completely deterministic. It will be just some probabilistic time that we will be using, and more if this probabilistic time when we obtain this probabilistic time, it will give us this insights into the mobility of this material, how fast these electrons can move in a particular material. So this simply, as someone rightly said, there is some relation between this tau as well, which is given by this. If we say this mu naught is the mobility, and this q is the electronic charge, and tau is the mean free time divided by m star. Now this m star is the effective mass. This effective mass also plays a crucial role in governing the whether the material will have fast moving carriers or light moving carriers, because it is intuitive to think like this, that if I am having a heavier object, for example, I have to move it, I have to push it from from point A to some point B, covering some distance x, then if the object is heavier, it would offer me more resistance as compared to a lighter object, which I will just push, and it will move from this point A to point B, and it will cover this distance x in some desired amount of time. So this mobility, you can say, is inversely proportional to this effective mass, and we will see this effective mass briefly, and it is directly proportional to this tau. So it means more the amount of time between these mean free time between the collisions, the more will be the mobility. Now this mu naught is given to be equal to, this value is given to be equal to q times tau by m star. Now this ek relation over here is simply a plus b times, these a, b, and c are constants, it has been mentioned, b times k minus c whole square. Okay, so now if we consider this this ek relation, we will see that this m star is given by h bar square, okay, by this value, which is d square e by dk square. Okay. So this d square e by dk square is basically the, stay tuned. Stay tuned wants to join. I don't think it's some student, but let's admit him. Okay. So this m star is M star is simply this thing which we said that this is it is the second derivative of this ek relationship that we will be having. This e this now we will be required to derivate this thing, this ek relation, and you can see clearly from this it will just be 2 times k. It would simply be 2 times bkc. So if I derivate it first time, it will be simply de by dk. It will be 2b k minus c. Okay, and then if I derivate it again, it would be simply de by dk. It would be 2 times b. Now if I put it in this kind of a thing, so it would be m star is given by h bar square by 2b, or simply this will be given by mu naught is equal to qt into 2b by h bar square, or simply mu naught h bar square by 2qb is the mean free time for the collisions. Now let's check if it matches some option. Mu naught h bar square, okay, by 2qb. So the option C is the correct option for this. Now uh, this this kind of a problem, these kind of problems are always interesting because they always confuse us whenever we try to compare two quantities, when one is increasing and one other is decreasing. They usually students get confused with these kind of things. Now this similar kind of concept over here, when we see a particular material, it would have this as we said previously, that there would be this electron interactions that would result in the collisions. Let's not call it electron interactions because it would be a vast term for that. It would mean a lot. So let's say that electron collisions, this electron collisions, whenever they happen, they result in the degradation to the mobility. Similarly, there are these phonon vibrations that I shouldn't say phonon because you might not have some. Uh, you must have seen this spring mass system where this one, let's say I have two balls which are attached to each other by some spring, and they constantly vibrate with some if I give them some kind of a force, they constantly vibrate to some extent, to some point of a time, with this force that would be acting on them, that is kx. They will be having that opposing force. That similar is the case with these, we can say, with the atoms. If I have two atoms, I can consider them as a spring mass system, let's say. So if they are given some energy which is always there at the room temperature, for example, let's say, then these atoms will be vibrating a bit. So this vibration will cause the mobility to decrease. So more this vibration, more the degradation in the mobility due to these vibration of the atoms. Similarly, if I have I have doped some material, let's say I have silicon and I have used some impurity to dope it, then after doping, this doping atom will have its it will be positioned. Wait a second. So it would be positioned somewhere in the lattice, and it would also act as a scattering site. So it would also try to manipulate the moving carriers, for example, that are going from the source of a MOSFET to the drain of the MOSFET. So it will try to manipulate its path. It will try to affect its path. So these both these kind of things, that is this lattice vibrations and these impurity ions, they both try to interact with these moving carriers and try to change the or affect the mobility or the motion of the transport mechanisms. So basically over here, it it is being told that this some silicon material, say some silicon material consisting this electrons of of electrons is doped, and due to this doping, this there is this interaction scattering with these impurity ions. And also we have been told to consider this lattice vibration motion, and as a result of which, but now there is one twist. We have been told that this lattice vibration, we have to look into it when the temperature is low. You must have heard these days that people are working on cryogenics. This cryogenics, that they are going to the liquid nitrogen, liquid helium temperatures for the studies. So basically, if we simply consider some device, uh, you must have heard that uh, if some of you have might have done this UG course of this regarding this device physics or this MOSFET thing, you might have heard that this subthreshold slope is limited by the Boltzmann tyranny. At room temperature, we cannot get below this 60 millivolt per decade. So this 60 millivolt per decade subthreshold slope, this thing hampers the application of these materials as fast logic switches. For if there is some transition that is happening quickly, let's say this subthreshold slope is nothing but it is this transition from the on state. Let's say this thing, for example, I have this some curve which is in the log scale. Let's say this is IDVG curve. So this thing from this IDVG at some particular VD, this thing, this transition which let me draw it in red. This transition from this off state, if I consider this to be as off state, and if I consider this to be as the on state, this transition from the off state to the on state, the slope for this thing will be greater than 60 millivolt. So this thing will not allow us to quickly switch between the off state to the on state. So as a result of which, we will be having this we will be requiring more change in the gate voltage for to change the current by a particular amount of magnitude. These things can be significantly improved at the cryogenics, lower temperatures. As you will see, this subthreshold, these characteristics are proportional to the temperature, and when we decrease the temperature, this kind of a thing, this subthreshold slope, this also goes down. So this is one of the advantage of using materials or using these devices at low temperatures. It enables us to save the energy, because we will be having efficient switches that will be switching from off state to on state, let's say within within a zero point 0.0 or 1 volt change in the gate voltage. Although that is very hypothetical that I am talking, but still these things can be achieved at cryogenics, that is low temperatures. Now this at low temperatures, these lattice vibrations, they will be really less, because we know this thermal energy, which will be kT, which we always say that it is 26 milli electron volt at room temperature. We keep on saying that because this temperature has gone down, this energy will go down, as a result of which we will be having less thermal vibrations. But the problem now is, since this motion is less now, this these carriers will at low temperature, very low temperatures, they will have to spend, we can say this is a conventional definition, every time we are being told these kind of things, that it will spend more time in the locality of this impurity ion. Now we have been told that we are in low temperature region, okay, and also in that low temperature region the temperature is increasing a bit, okay, the temperature we are increasing, as a result of which, since this lattice vibrations are gone at this kind of a temperature, but this ionized impurity scatterings, they are present, and they are mostly predominant than these lattice vibrations. But at that particular low temperature we are now increasing a temperature. You must have seen that there is some mobility curve, like looking like this, this is a mobility curve with the temperature. So if this is the temperature, this is the mobility, okay, but let's not go into this because it is too soon for this. So this kind of a thing, this means that this when this temperature is increasing, now the carriers, these transport carriers will have a less amount of time in this locality of these impurity ions, as a result of which the mobility will increase at this temperature, at low temperature, when we are increasing the temperature. So that's what we have written over here. At low temperature, the lattice vibrations will be mostly suppressed, and this scattering due to impurity low temperatures can be negative. Oh, what, Matthew? Can you elaborate? I don't understand the concept of this negative temperature. There is nothing like negative temperature. Okay, wait a second. Someone is knocking.
भैया इसका चार्जर हो और क्या?
ये कौन सा फोन है आपके पास?
ये जियो का फोन.
नहीं भैया, कौन सा वाला लगता है इसमें, फिर भी दिखाए. मेरे पास टाइप सी है.
टाइप सी है.
वो नहीं लगेगा. ऑफिस में देखिए. हाँ. Yes, Neeraj. So, can you? No. Negative temperatures. There is no such concept that I have heard of. To my knowledge, I have not heard of such things. But you can explore, and even I will explore after this. I will try to see what you are saying, but to my knowledge this is not feasible, these kind of things. But it has been shown that MR magnets, what you mean by MR magnets? Okay, negative temperatures. Let me see this kind of statement, because I don't know whether this is electronically feasible, because going to the 4 Kelvin itself is a huge task, and it requires huge amount of setups for characterization, etc., and going to 0 Kelvin is even really tough, because then we will be having superconductors around ourselves. If it was so easy to go to the 0 Kelvin, let's say, or these 4 Kelvin, because many superconductors have been pruned at these kind of temperatures. But since these temperatures are not feasible enough, and I don't know about this minus thing, I have no idea about this. So let's explore this after the class. and if I find some interesting thing about this, I will try to mention it in the next lecture. Fine. So this mobility now, this mobility will increase at this low temperature due to the due to this very few scatterings, due to the very few lattice vibrations that are happening, and as a result of increasing the temperature, these impurity interactions, the interactions with the impurity ions also decrease, as a result of which the mobility increases. Now let's move towards another problem, where uh, it has been told that this we have been told to consider 1D lattice, 1D crystal lattice with some lattice constant equal to A, and the crystal length, which is the total length of the crystal. For example, uh, I am having 10 nanometer crystal or 20 nanometer crystal in length, and the lattice constant will be the spacing between the two atoms that is lying within the crystal that the particular this crystal is being constituted of. For example, if I am having silicon, the distance between two silicon atoms will be denoted by this A, and the total length of this material, total length of this bar of silicon will be denoted by L. This will be the crystal length. So where do you observe these energy band gaps on the energy dispersion graph? Now you all must have seen this chronic penny model thing, and you must all have seen that how these energy band gaps evolve, and let's not go into that particular thing, and let's not move to these what we can say, these diffraction kind of things. And you must have seen that when we solve this chronic penny model, which is basically this thing. For example, if I have wait a second, if I have some atom over here, if I have some atom over here, some atom over here, continuously I am having this periodic arrangement of atoms, as a result of which I will be having some potential due to these atoms. Let me draw this potential first hand like this. This will be the potential, this will be the potential due to this atom, this will be the potential due to this atom. Kindly be aware, my drawing is not that good, so these might not be looking symmetric to you, so that might be a problem because these potentials will be completely symmetric. Wait a second. So let me say that it is like this. I think I have made it wrongly. Yes, I have made it wrong. It should be like this. Okay, okay. So it should be like this. These atoms basically, they are basically, this atom is interacting with this atom's potential, as a result of which the average potential would look like some sort of a, this we can say like a parabola, to be to make everything convenient. And this kind of a thing over here, this will also look like some parabola, and this kind of a thing will also look like some parabola. So we would say that this kind of a thing resembles somewhat to that of the potential well problem that we did in the previous we can say previous sections, that professor also told in the class that we will be dealing with these potential well problems, and these potential well problems provide insights into the energy bands that we will be getting in the future lectures. That was the main motivation behind studying that particular configurations for these potential barriers. So if I try to approximate this thing, it would look like this. Okay, it would look like this, let's say. So it is some periodic arrangement of those potential wells that we had seen, that finite potential wells, when we saw the quantum part of this course. And as a result of which, if this is some atom, this is some atom, this was some atom, this was some atom, and as a result of which we solved this Cronin Penny model, uh, to get the insights into the how this energy of the material changes with the momentum space, changes in the momentum space. And as a result of which, we found that if these materials are having some spacing between two atoms, which is denoted by A, which would be simply the Let's constant. The professor must have told that how we will be obtaining this left hand side and the right hand side of this particular expressions. And for that, we will be limiting our solutions by using the properties of cos and sine, that it would have its solutions lying between -1 to 1. Wait a second. It would be having its value lying between -1 to 1, and as a result of which we will be getting these. Wait a second. and and as a result of which we will be getting this energy band gaps. And this Cronin Penny model helped us to get brief insights into that. Basically, this is just the simplified assumption of this particular kind of a potential well that we have drawn over here. So this Cronin Penny model in 1D provides some insights. So now these energy band gaps, as you might have seen in that these things occur at the Brillouin zone edges. So simply it would be the answer to this problem will be n pi by a. Although we can go much deeper into this, but let's say that this latest spacing, what we have seen in the previous lectures as well, that this latest spacing between these two things, they when we use that boundary conditions in the finite well problems, we saw that we got it in the multiples of a pi by a, where this a was the length of these we can say this small box. That small box was basically the Let's constant of a particular atom. Let's consider it that way, so that this problem you won't get confused any time about this problem. So you consider these as small infinite finite well potential boxes, and as a result of which the k would remain this n pi by this would be multiples of having the integer multiple of n pi by a. Now this Brillouin zone, we can say this if for example I am having two atoms. Let's say for example I am having atom A, and I am having similar kind of a atom in its neighborhood in the 1D kind of a system. For example, let me draw it in 1D, and this is some material which is having its two neighbors in 1D, and as a result of which we have been told to find its for example Brillouin zone. So in order to find the Brillouin zone, you must have seen that this silicon has some rhombohedral sort of a thing as its Brillouin zone. So or how that kind of a thing is made is simply by drawing the perpendicular bisectors to the neighboring atoms. So if I am having these two neighboring atoms, they will be lying in some plane. For example, let's say this x plane, and I will draw the perpendicular bisector on this plane, which would be just in the middle of these two planes. Similarly, for this left hand side, I will be having this what we can say a perpendicular bisector on the another neighbor, and as a result of which this thing that we would obtain would correspond to the Brillouin zone of this material. This will be the its first Brillouin zone, considering the uh, its nearest neighbors. So similarly, when we solve for this silicon by considering these planes, these outer planes, for example, we'll draw the perpendicular bisectors, and then we find that where it is intersecting these points, this point of intersections, and then we connect those point of intersections, we will be able to obtain some this kind of a zone, which would be basically it is given known by the name of this Wigner seed cell, and you will be having this kind of a region or a zone which will be known by the name of Brillouin zone. So this Brillouin zone basically it is a region in the K space where it contains the solutions to these wave equations. So the simple answer to this would be answer A, because rest of the options you can say that a region of position space where electrons can reside within, it isn't, and another name for the unit cell. So these options are not matching, and the only option that is of particular interest to the Brillouin zone is this, that it is a region in the K space where we have these equations, solution to these wave equations. And this Brillouin zone, you can draw it for example 2D material as well. If yes, K space means reciprocal lattice. Yes. What kind of explanation do you need? Okay, it okay, thanks. Let me add some points to this. For example, if I am in time domain, I go to frequency domain, that is the Fourier transform. Similarly, I am in the direct space, I go to the reciprocal space. You can consider it as a Fourier transform. Basically, it is a Fourier transform, but getting into that particular what we can say in particular element of study will only complicate the things, since uh, let's say that these are two quantities which are transforms of each other, like time to frequency. Similarly, we have this kind of a thing where we have direct space lattice and reciprocal space lattice, and this K space, this reciprocal lattice space lattice, what we were saying, that we can obtain it for 2D, similarly by drawing these perpendicular planes. And uh, now let's see, this is some this is also related to this band structure. This is a different kind of a problem, where we have been told that this band structure is having some relation between energy and this momentum space, that is this k vector, which is given by h bar vf times kx. This kx is the, as you can say, this reciprocal space lattice vector. Okay, now this says that we have to find the effective mass for this thing. If we are going to find the effective mass thing for this material, it is known to us that we should be having this second derivative. Now this, for this particular material, if we concentrate it on this material, okay, Monica wants to join, I don't know. Okay, so this kind of a material, uh, consider the 1D structure. So this has some relation which is given by E times h bar vf kx. We can clearly say that this will not be having second derivative. This will not be having second derivative. So this for this kind of a material, the effective mass will not be they does not exist at kx equal to 0 simply, and the effective mass is not defined. Now you may get confused that if a material is having, for example, infinite effective mass or zero effective mass, let's say, how is it possible? If we consider this graphene, this 2D material, where we have the relation between this energy and the k, and this point corresponds to the Fermi level, and this is the valence band, this is the conduction band. You would find that for this particular material there is no band gap. That is the first thing, because this valence band and conduction band are not separated, and also they, due to this flat kind of a nature, this since we can clearly see that this is having some line equation, which is y equal to mx something, if we consider this to be 0, let's say, and as a result of which its second derivative won't exist. So how do we study this kind of a material? Basically all these kind of materials, the band structure contains the all the information that we are going to need while doing the device transport simulations. So this effective mass kind of a thing is just for the ease of understanding, because if we also see, for example, if you can go to this silicon band structure, for example, or any other material band structure, let's say, let me draw some hypothetical band structure which you must have seen, that for we will, when we draw the band structure for this free particle, which has been confined, now we will be having these corners which will be bent sort of. This bending here I have shown is more prominent, it might not be that much prominent, and when we try to characterize this kind of a material, we use this parabolic band approximation to find the effective mass. We say that this material in the vicinity of, for example, this conduction band minima CBM is the parabolic in nature, as a result of which I try to fit it with some parabola. Let's say I have fitted it with some parabola like this or like this. So as a result of which we will be having effective mass which would be dependent on the some fitting procedure. So we will be saying that this particular material has a particular effective mass based on some particular approximation, which is based on the considering that the material is having some relation, which is E is directly proportional to K square, something like that. So we are considering this material in the vicinity of this conduction band edge, or so for example valence band edge, to be parabolic in nature. For this approximation might not be valid for the materials having linear dispersion, or for example I will be having some flat band like this. I will be having some flat band. So when I try to approximate it with parabola, I will be able to approximate it within a particular energy range. Let's say, for example, this is 0.1 electron volt, let's say. So I will be able to fit it in only 0.1 electron volt. Above 0.1 electron volt, I will not be able to fit or characterize a particular material's band structure, as a result of which, if I am using this material approximation, this effective mass approximation, to represent this band structure, I will be either overestimating or underestimating its device characteristics. So this simply means that this effective mass kind of a thing is approximation that makes our life easy, or that helps us to check whether a particular material is having, let's say, is having a heavier kind of a band structure, we can say, or lighter kind of a carriers in its band structure. That's it, and nothing more information can it convey. It can only convey these kind of things. And this linear dispersion, although this might not have this effective mass defined for itself, but still, since it is a band structure, it would have all the information that's required for a particular transport calculation or device characteristic calculation. So this parabolic approximation was just a tool that we are not able to use on this linear kind of a thing. Otherwise it has nothing to do with the failure of the physics. The physics stands there. Physics is that if we have to calculate its characteristics, we will be able to calculate its characteristics. There is nothing like this effect, that if I'm not having this effective mass, and I will not be able to calculate the materials properties. Now this is also related to this Bloch's theorem, and I guess you might have done this. And it says that this Bloch's theorem, for a periodic potential, we have seen that this potential over here, this was periodic with some period a. This is a periodic potential, and this periodic potential is for this Bloch's theorem says that the wave function is given by, at some point a, which is a lattice constant, it is given by psi x e to the power iota k a. Okay, it has to do with the probability only, because the probability at x equal to 0, let's say, and x equal to a has to be the same one and the same thing for the periodic lattice. Now for this kind of a problem, we have been told that this ux uh, ux is also periodic in nature. Okay, this ux is the periodic potential that we have seen previously. This ux is periodic in nature, as a result of which this u of x plus a is u of x. So this makes our life easier for these periodic kind of things. So now we can say that this psi of x is also equal to, uh, you can say psi, let's calculate for the psi of x plus a first. Psi of x plus a is simply psi of x e to the power of ik x plus a. Sorry, this has to be u of x plus a. Fine. So it would mean that I have to evaluate it for psi of x plus a, which is simply u of x plus a is simply u of x, and it would be simply e to the power iota kx, and it would be e to the power iota ka, and psi this but we know psi of x is simply u of x e to the power of, okay, e to the power of iota k x. Okay, so it would mean that we will be having this equation to be equal to iota ka. This would simply be equal to psi of x plus a is equal to u of x plus this thing would simply mean that I have got this thing to be equal to psi of x plus a. This would be simply psi of x, and this would be simply e to the power of iota kx. Okay, so uh, we have got this to be equal to, okay, I guess this is not matching, u of x, this is not matching any option. Where have we done the wrong thing? Psi of x plus a U of x is simply U of x. Wait a second. U of x of a is U of x into e to the power psi of x, U of x into psi of e to the power. Can anybody comment where we have gone wrong? Okay, this was an assignment. I got this answer wrong in the assignment. The correct
Actually,
answer.
the answer for the assignment was option D, sir.
Oh, no, no, no. I am saying, why am I getting psi of x e to the power kx? That's why.
Since x plus a equal to x.
Oh, wait a second. Wait a second. My option is not matching with any answer. That's why I'm confused.
We
Psi of
equate the two equations, sir. It cancel out.
which equation?
Psi of x e power ika is equal to u of x e power ikx into e power ika. Then e power ika both cancels out. So psi of x is equal to u of x e to the power ikx.
Sir, in the third line you can equate the psi of x plus a expression, sir, as they pointed out.
Okay, okay. Okay, I have written it to be here. U of x e to the power ika. But
Sir, the red color equation LHS can be equated with this, sir.
you are saying this equation?
Yes, sir. If we equate, because since this equation is also represents psi of x plus a, we can equate and we will cancel out the e power ik. Sir.
You will just get e to the power ika equal to this e to the power ikx.
Yeah.
But that's not. I was looking.
But the question is about psi of x plus a, not psi of x.
Let me do it again. This is psi of x plus a is simply psi of x. Let's skip this equation. U of x plus a is u of x, and psi of x is simply psi of x is simply psi of x e to the power. Psi of x is simply u of x e to the power I k x simply, and psi of x plus a is psi of x plus a is u of x plus a e to the power x and e to the power iota k a. Okay, so it is simply psi of x is simply u of x e to the power I k x. Okay, fine. Yes, yes, yes. It's option D. That is the correct one. Fine. Okay. You are absolutely spot on. Thank you. Mm, yes. Okay. Now let's move towards another problem, which is regarding this body-centered cubic structure, which says that this let's constant, this body centered cubic cell is having this let's constant for this MO atoms to be equal to 3.147, and this radius of these MO atoms, this is one half of the center to center spacing between the these nearest neighbor atoms, we have been told to find the percentage of this cubic volume with that these ammo atoms will occupy. Now this body centered, this would simply look like this. This is the body centered cubic cell. Let me say that this is the, for example, if this is the lattice spacing A, this will also be A. Okay, this would be simply this would be simply root of 2a. Yes, it would be simply root of 2a. Now if we consider this is the phase diagonal, that would be root of 2a. Let me write down this phase diagonal, because then it is hard to recapitulate the things. Is equal to root 2a. Fine. And now this cube diagonal, that will be having k, that would be having this thing as this its hypotenuse. This thing, let me draw it in red. So wait a second, let me draw it in red. This thing will be its hypotenuse, and it would be having its sides to be equal to a and root of 2a. So it would mean that this cube diagonal will be simply having this hypotenuse to be equal to root 2a square plus this root 2a. Wait a second, this a is not under this, this is root 2a. So this will be 2a square plus, we will be having a square, and it would be simply root 3a. Let's write it down clearly so that it doesn't look under this square root. So it is root 3a. Now we have been told that this is, since this is a body centered cell, so if we consider these ammo atoms which are lying, let me draw it in another color. Let me rub this first. These ammo atoms, if I consider these corner atoms, they are touching this ammo atom, which is the case, which is always the case. So I will be having this distance. It has been told that this center to center spacing between these nearest neighbors, this center to center spacing will then become, this is one center, this is another center. Okay, so this center to center spacing will simply become root 3a by 2. So this is the center to center, center to center nearest neighbor spacing. Okay, fine. Yes, this is the center to center nearest neighbor spacing, and this, if it has been told that the radius is half of this center to center spacing. So this ammo radius, this molybdenum radius, wait a second, this molybdenum radius is radius of ammo is half of this thing. It would be root 3 by 2 divided by 2, or it would be simply root 3a by 4. So this is the radius of the ammo atom. Now this volume of this ammo atom, considering it to be the spherical thing, 4 by 3 pi r cube, and r is given by this root 3a by 4. It would be 4 pi 3 by a root 3, it would simply be 3 root 3 a cube by 4 into 4. It would be 16 into 4. I have written it like this so that this and this cancels with this, and I would be left with one more mistake. There is only one pi, so I would be left with pi root 3a cube by 16. So this would be the volume of one ammo atom. Now we know that this BCC total has in total has two atoms. So this number of atoms is 2 for per unit cell for the BCC. As a result, this total volume occupied by this MO, total volume occupied by this MO is molybdenum, simply 2 times the volume that we obtained, because we will be having 2 atoms per unit cell for this BCC. So this is 2 times the volume, so it would simply be pi times root 3 a cube by 8. Okay, am I wrong? No. Okay, I guess it's fine everywhere. Okay, now we have been told to find its percentage of the cubic volume. So this percentage of the cubic volume would simply mean that this we have to divide it by the a cube. So this percentage volume of this cube occupied by this MO would simply be this volume, this total volume divided by this a cube into 100. So since we are doing we are looking for the percentage, so it would simply mean that this would be equal to pi. Okay, yes, somebody raised hand.
So
Hmm.
for radius we are dividing by 2, right?
Yes,
So it would become 2 root 3 by 2 a by what? But why are we putting root 3 by 4?
we are dividing by 2. Okay, fine. Root
Dividing
3,
by 2 means into 1 by 2, or like dividing the whole value by 2?
dividing the whole value by 2, because this radius is half of that thing. For example, if I am having 5 some value and as a diameter, for example, the radius will be 2.5, like that.
Yes, sir. My question is for division, when we are dividing by 2, and if there is already a denominator and we divide the whole value, won't it go to the numerator?
No, no, it's
That's what
correct.
I'm asking.
No, 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 it's correct. I am just root 3 by 2 a multiplied by 1 by 2. Okay, it is just the half. Okay,
Thank you, sir.
okay, fine.
That's what I was asking.
Okay, okay, fine. No problem. So it would mean okay, where were we? Acha, root 3a cube, and a cube will go. It would be simply pi root 3 by 8 into 100. So it would be pi into root 3 divided by 8 into, okay, okay, I will do. इसको क्या हो गया into 100. Okay, it is approximately coming out to be 68.01, approximately equal to 68.01%. So it would mean that yes, yes, option is matching. So it would mean that the option C is the option that we should go with. Now, as Neeraj said, that how we should be getting this. Achha, okay, can you once again how we got the cube diagonal? Okay, so let me draw it again. This, if this is some cube, let's say this is some cube, and let me use another color. This is the spacing between these two atoms, that is lattice spacing, or over here you can say this corner to corner distance is a, this is a, and if I use the Pythagoras theorem, simply it would mean root, this hypotenuse is equal to root 2a, root 2a, not a is not under this square root, root 2a. Now this is also a. Okay, now this body diagonal would mean that I am going through this point and directly going to this point. Okay, Consider this as a plane. If there is another color, yes, there is another color. Consider this as a plane, this thing as a plane. Okay, this if I consider now this thing as a plane for this body diagonal, this this would mean that this body diagonal is simply this hypotenuse, which is the body diagonal, is simply equal to root 2 a whole square plus a whole square under root. So it would be simply root 3a. Neeraj, am I clear? Okay, sir. Fine, thank you. Okay, uh, let's move towards, yes, this is another, yes, this is the another problem, that this band structure, this state which band, uh, let me ask you this question first, that if I am having this conduction band profile like this, which is shown over here, uh, which will be having this heavier electron effective mass. You can unmute one by one. This the Tanish, you can unmute. You can comment on this. Okay.
I
Can
really,
hmm?
I don't, this concept, sir, I don't remember right now.
Okay. There's no problem. If anyone of you remembers or would like to answer, he
Sir,
can.
even though I want to ask one question,
Hmm.
in that Bloch theorem's question,
Hmm, 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 hmm.
uh, I am unable to create a relation between multiple representation of Bloch theorem.
Okay. I also got confused. I don't know why, but let me check it again with myself.
Okay.
When I will try to solve it again after this class, and I will update it in the notes. Uh, if I would myself try to check this relation, that whether I am able to get this again or not, because
Okay.
I myself got somewhat kind of a stuck in this relation, but I think we arrived at the end at the correct relation. But let me write down the steps. I will write down this detailed steps after
Oh,
this session is over, so that I myself, when I see these notes again, I just by just seeing into this, I just find that this is the correct way to go through this, because
okay, no problem.
currently in here it is also looking somewhat, I think, shady.
Mm, yes, sir.
Oh, okay. We were discussing about this question. Sorry. So this question,
Sir, I think the A curve will have higher effective mass when compared to B.
higher effective mass with respect. Any other answer? Thank you, Shrihari. Any other answer? Just answer the question, whatever you feel, and I will just. Okay. Somebody has unmuted.
I also think A curve is known. Like it
Uh,
has higher electron effectiveness.
can you just give me some logic behind this? What could be the
Because
reason?
wider band means scattering will be wide, right?
Scattering?
Scattering or the torque will also be uh, like scattering effects will be higher, I think,
No,
right?
no, no, no. Don't go into scattering. Don't go into scattering. That has to do with the k vector, not this thing. You,
Oh,
you, you just see what is the relation between effective
if
mass?
scattering increases,
No, no, no.
effective mass decreases, right?
Nee. Scattering has nothing to do with effective mass. Scattering has to do with the effective mass, but effective mass has nothing to do with the scattering. You can say it like this, that effective mass won't change with scattering. if I am looking at a particular curve, for example this parabolic curve, if I am at a particular CBM, it would remain there till the whole time. It would be having the same shape. Only the carriers will move from one point to another point. For example, this is some really good thing. That for example, if I am over here, let's say, and if I am over here, these both things will have different kind of effective mass things. uh, if I try to fit it by some parabola, so that is there. That's also that you can, that what you are saying, that this thing that uh, if I am having this scattering, then this material will have this electron from. Okay, Tanish, you can also join in. Okay.
Sir, is this the B band is having the heavier electron effective mass?
Okay, fine, thank you. Neeraj, you can also unmute.
Sir, B will have higher
Okay, thank.
because
Okay.
we will be we know the EK curve, which is
Okay.
having the length of pi by a,
Mm-hmm.
and in those terms I think B will be the heaviest.
Mm-hmm. Okay, fine. Coming back to this question from Asha, that for example, if I am having this is some really nice question that she tried to answer. For example, if I am having some material which is having this band structure like this, for example, okay. Now, this some scattering or some phenomenon happens, that there is this translation of this k vector, that this particle, this material, for example, is excited and it moves to this state. Let's not consider this state first, because this will be having negative effective mass. Let's not confuse ourselves with this thing. So if we say that this, there is some translation in the k vector, and as a result of this momentum conservation, we went to this particular place, and this particular place, for example, if I try to fit the parabola for this region, for example, it would be having some slope y equal to a1 x square. Okay, so this when I fit this kind of a thing, for example, this will be having y equal to a2x square. Okay, so when I am fitting these band structure regions, or band this conduction band regions with these parabolas, I am getting different slopes. So it means that when this event has happened, that when a particle is excited, or when the particle has moved from Manikandan wants to join. Okay, admit all. Okay, then when this particle it moves from a region where this curvature of band structure is different. For example, in here, in point, at point A and point B, at point A we had one kind of a curvature, and at point B we are having another kind of a curvature, then this effective mass changes. So it is this position dependent thing. This region will have different effective mass, and this region will have different effective mass. So in that sense, it is you can say. Okay.
Okay, sir. Thank you, sir. So
Yes.
yeah, so what you are saying is, when the regions change, the effective mass change. It is
Yes.
not because the effective mass change that the regions change, right? It is
Yes.
not
Yes.
the
Yes.
other way around. That's what you
Yes,
are saying,
yes,
right?
yes. Because you have seen that this band structure of this gallium arsenide, you see that there is some little space, what you can say, in the energy spacing between this lowest conduction band minima and the second conduction band minima. That's why in gallium arsenide you get this peak in the velocity. When you draw this mobility versus electric field, you get some peak in the velocity, and you get this another peak after that. So this is due to this thing, that this transition happens, that the carrier moves from this lowest conduction band minima to the second lowest conduction band minima, and its characteristics change altogether. Okay.
Okay, sir. Thank you,
uh,
sir.
so this is some really nice observation, we can say, because these kind of a things, that they matter to us in device characteristics. You must have seen these band structures where these transitions occur. from due to this, we can say, thermal excitation or some kind of a thing, that this gallium arsenide, which is having very less spacing between the two separated minimas, they can show completely different properties, not completely different, they will show, let's say, improved properties, or they would show degraded properties. For example, if this is a low mass valley, for example, if I am just hypothetically saying that, and this is a high mass valley, for example, then if this transition has occurred, for example, the carrier has moved from this low mass to high mass valley, this would simply mean that the mobility in the high mass valley will be less. So this will result in the degradation of the mobility. That's one case which is possible over here. Now as we were all of you answered this question, and I was happy for this, that you are having some concepts regarding these band structures, because this band structure is the penultimate thing that you need to know. Band diagram and band structure, these are enough for you to understand the device physics. So this problem, as some of you rightly pointed out, that in these kind of problems, we simply say that we consider this parabolic approximation first, and we say that this m star, which is the effective mass, we always use, whenever you must have seen that the professor using effective density of state, effective mass, because this actual density of state is some other thing. When he uses this term effective density of state, he considered all the states that were present above this conduction band to be lying at the conduction band edge. He said that it is the effective kind of a thing, just to we can say ease our calculations, nothing more than that. So now this m star is h bar square by d square e by dk square. So whenever we see any kind of a curve where we have been told to find the effective mass or comment on the relationship between the two curves, we just need to look at its slope, how fast the slope is changing. For example, second derivative is changing. For example, if we see this material A, will have this second derivative to be greater than, let me write it as A, let me write it as B. So this would have this second derivative to be greater than this you can say this curve B. This is simple. For example, if I am considering this y equal to mx solution as well, if I consider this slope and this slope will be greater, this will be less. Okay. For example,
then the slope of B only should be greater also.
okay, slope of how? Yes, Srihari, you can unmute.
So nothing, sir. Okay, sir.
Okay. No, you can ask. You are free to ask any question. I enjoy these kind of things. These okay. So we were saying that this d square e by dk square will be having a more slope. So it would mean, since this is in division, this is more thing and this is less thing. So if I divide this as some constant value, this is the Planck's reduced Planck constant, if I divide it by some more value, it would mean that this value corresponding to m star A will be less than m star B. So it would simply mean this effective mass in case of these we can say this A is less than the effective mass of B. Now let's simply use this simple intuition. So it simply means more the bands, more the flatter the bands, more if we are having more spread in the bands. For example, if I am having a structure like this, it would mean it would have more effective mass compared to this, which is a steeper thing. This steeper thing It means that this material will have less effective mass. So just by looking, whenever we see any kind of curves like these, we can easily say that this material which is having steeper curvature, it would have less effective mass, and material which is having the flatter band structure or flatter curvature will have more effective mass. But one should remember that these kind of things only hold true when we are considering the parabolic band approximation. So I guess that's fine for this question. Now we have been told to uh, okay, fine. We have been told to look into the energy band diagram, and we have been told to find that the electric field that is associated with this energy band diagram. How can we find this electric field from by just looking into the we can say shape of the energy band diagram. Let me be clear again that these energy band diagrams and these energy band structures, you should try to devote some time on these kind of things, so that because we can say everything in semiconductors happen at the interfaces. And this when for example I am drawing the p-n junction, which we will see in the upcoming lectures, that I will be having p-type material on the one side and n-type material on the other side, and when we join these two, not like join kind of a thing, it is fabricated. I am just using it this term join. It might sound this thing that we will be just joining these things, but let's say that we are fabricating this material by depositing, let's say, n-type material on this p-type material, as a result of which we will be having this interface between these p and n junctions, and all the we can say interesting phenomenons all the interesting phenomenons will happen at that particular interface which lies close to the this p and n junctions. So solving these energy band diagrams and looking into these energy band structures, you can get deep insights into the device physics just by looking into those things. Now you all must be knowing that, for example, this electric field, if I consider in 1D, this 1D case, this electric field is simply equal to minus dV by dx. You all know this. E dot dl, integral of E dot dl is v, that we all have studied previously. Now, this energy band diagram, basically it is the representation for these electrons, how these levels, these energy levels of these electrons are in the material, how they are they are present in the material, how this electrons energy profile looks inside the material. It is just the representation in the we can say in the direct lattice, you can say in the direct space. So if this electric field is given by minus dV by dx, and we know that for an electron, this E, this is this electric field, sorry, this is the electronic energy. It is simply given by this minus qv, where v is the potential. Now this if we take this some reference, this ec as the reference, because choosing any reference coordinate is up to us. So let's say that for example we are choosing this conduction band edge to be the reference. So this ec is the reference, ec is the reference for us, for example. So it would mean simply that this E is, this electric field is simply equal to minus dV by dx, or it is simply equal to minus d by dx of uh, minus EC by Q, since we have taken this EC as reference. Okay, This is the conduction band edge. So it would simply mean it is 1 by Q, because this Q is the electronic charge which is the elementary constant, is equal to dEc by dx. So this this gives us this electric field is proportional to the slope of this conduction band edge. So this was one simple thing to look into the electric field, how we can look into the electric field. Now let's move towards another problem where I have been told that we have this n-type semiconductor, and this n-type semiconductor is at 0 Kelvin. So we have been told to find this Fermi level in the material. So let me ask you, uh, where you would say that the Fermi level would lie. Material is n-type. One second, Neeraj. Material is n-type, and you have to consider the material at 0 Kelvin. Okay, Neeraj.
Between the donor level and the conduction band.
Absolutely, Shri. But please give me the logic behind this. Anyone, not only Shri.
Since it is N-type semiconductor,
Mm-hmm.
generally the Fermi level will lie above the intrinsic Fermi level,
Yes. Okay.
and all
Absolutely, Shri. Some other person can also answer. Carry his statement forward. This is really a nice answer by Mr. Shri. He said that this for this material, if I am having n-type material, I will say that this Fermi level will lie above the intrinsic Fermi level, or the mid of the gap. It would be closer to the conduction band. So that is one thing he absolutely pointed out. And another thing is that this temperature is given to be equal to 0 Kelvin, that we need to account in this problem. So this is a really nice problem said by the prof. Uh,
Sir,
okay,
sir, donor level nearby conduction band would be there.
okay, fine. So what would it mean?
Means it would be donor level where it would lie.
You are saying it would lie in the donor, but there is no option. Which option are you selecting, Vinod? Mr. Vinod?
It's a means B nearby conduction band.
This is inside conduction band. It means inside the conduction band. Would it lie inside the conduction band? Because inside the conduction band would mean,
So it would be, would it donor level or would it inside conduction?
okay, you are saying that you are confused between B and D.
Yes, sure, sir.
Okay, fine. So it would mean that we need to take account this definition of these Fermi-Dirac statistics first. That Fermi-Dirac statistics. Let's say that since we are at 0 Kelvin, we are at 0 Kelvin. So it would mean that this Fermi-Dirac statistics. Let me write it down like this: Fermi-Dirac statistics. It says that the all the states all the states below the Fermi, okay, Wait a second. Below the Fermi level or are should be filled with electrons. Now this is point number one. The second point is that we need to take into account while solving this problem is that no dopant atoms should be ionized or could be ionized due to the temperature, that is this 0 Kelvin.
Sir, the other reason for the presence of Fermi level between donor level and conduction band is freeze out.
Okay.
That means at 0 Kelvin,
Hmm.
even though the electrons are near to the conduction band, it is due to the inavailability of thermal energy to conduct. So no electrons will be above the donor level and below the conduction band, but no electron will be present at the conduction band. Hence, the net carrier conduction is zero at T equal to 0 Kelvin.
Mm-hmm.
This state is known as freeze out.
Mm-hmm. You are somewhat correct, I would say, but I really appreciate this explanation. This was some real intuitive explanation for this. And since now this Mr. Srihari told that this there there cannot be ionization, complete ionization. Sorry, not complete. There cannot be this ionization of these dopant atoms due to this energy, due to the lack of energy. Uh, this means that these donor states are all filled with electrons. Thus, it would simply mean that since these donor states are filled, and we have to use the definition of this Fermi-Dirac statistics, which says that this all the levels below the Fermi level should be filled. It means that donor level has to be below this Fermi level. So it means that this Fermi level will be uh, close to the conduction band. That's one thing, but it would be above the donor level. So it would mean that this Fermi level will simply lie between this donor level and the conduction band. And let me repeat again, since this energy, this thermal energy is not sufficient enough for this ionization of these dopant atoms, as a result of which this dopant atoms cannot be ionized, so they remain in their donor level. If they are in their donor level, which is filled, completely filled, it means that we have to resort back to the Fermi-Dirac statistics, where Fermi-Dirac statistics says us that the levels or the states below the Fermi level should be filled. It means that the state above the Fermi level should be empty. As a result of this thing, it would simply mean that this Fermi level will lie above this donor level, and it will lie below this conduction level. So thank you for this explanation, and thank you for answering the question. Okay. Okay, Neeraj, you can ask. Yes, Neeraj. Acceptor level. Okay, where? Where is the acceptor level? Okay, you can. One second. You have written some acceptor level. Is it above the Fermi level? In this case, since we are considering it n-type, so you should not confuse with this thing. And while in this p-type material, you can be you can say this thing. This is absolutely what I guess you are trying to say. So yes, for P kind of a thing, this is the kind of a definition that you are trying to use is correct. Okay, fine. Thanks Neeraj. Thanks from my side also. Okay, now okay, let's move towards another problem since we have got more 11 minutes. Then you will join another session from our colleague. So it says that we are having this some intrinsic silicon, so means it has not been doped. It is this pure silicon that has been taken, and now it is doped with phosphorus atoms, and it has been doped with boron atoms as well. Now this phosphorus atoms, they act as donor impurities due to the valency of 5, and this boron atoms will act as the acceptor atoms, as Mr. Neeraj was saying that uh, about this acceptor levels. These acceptor atoms now are causing this material to behave like P type, while these phosphorus atoms, these donor atoms, are trying to keep it as N type. So let's take some effective doping. Effective doping. Effective doping. It would be P type effective doping because it has having this value to be equal to 6 into 10 to the power 16. It would simply mean I have Na, which is 6 into 10 to the power 16 per cubic centimeter, and Nd is 5 into 10 to the power 16. It would simply mean 6 minus 5 into 10 to the power 16 cubic centimeter. Okay, it would simply mean this p-type concentration due to this overall acceptor and donor atoms is 10 to the power 16, of the order of 10 to the power 16. Now this since this material, this silicon, is having Ni of the order of 10 to the power of 10, you must have seen this in the lectures that it has the intrinsic concentration of the order of 1.5 into 10 raised power 10 or 10 raised power 10 per centimeter cube. So this since this Na minus Nd that we found out is 10 to the power 16 and it is much greater than Ni, you can say that this 10 to the power 16 is much greater than 10 to the power of 10. Okay, so we would say this Na minus Nd is simply equal to P is Na minus Nd. It is the effective concentration of this holes. So this is equal to P is equal to 10 to the power of 16 centimeter per centimeter cube. Now using this mass action law, we can say this Np equal to Ni square or N equal to Ni squared by P. Let's take this Ni to be equal to 10 to the power 10 per cubic centimeter. It would mean this is equal to 10 to the power of 20, and it, since this P is equal to 10 to the power 16, we will get this N to be approximately equal to 10 to the power of 4 centimeter cube. Okay, now we have got this N and P values, that since we have been told to assume the temperature to be equal to 300 Kelvin, so it would mean that this thermal energy KT is 26 milli electron volt, and this intrinsic concentration we had taken. And one more thing that I forgot to say, you should repeatedly remember this approximation. This all the dopant atoms are ionized. So this has been clearly mentioned in this. That's why we have been able to take it completely equal to Na. We have taken the complete ionization of these carriers. Now this we have been told to find the location of the Fermi level with respect to the conduction band edge at 300 Kelvin. and we have been told to assume the effective density of states. That's what I was talking about. The density of states is uh, we can say it lies above the conduction band edge, and intuitively it should be zero at the conduction band edge, but we are considering it as an effective thing. Whenever we say this effective density of states, we say that the whole density of states is concentrated at a particular location, which is the conduction band minimum. Therefore, the ease of calculations, and this is valid up to a large extent. It gives us desirable results. So this NP and N and P we have found out. Now let us try to find out this the difference between this between the conduction band edge and the Fermi level. So we know this N, as we have seen it in the lectures. N is equal to NC exponential of EF minus EC by KT. It would simply mean I have to take ln on both sides. It would mean ln of N by NC multiplied by KT is EF minus EC. Okay, so it is simply 26 milli electron volt, which is 0.026. Ln of N came out to be 10 to the power of 4. Now let's look into the NC. NC is 2.82 into 10 raised power 19. 2.82 into 10 raised power 19. Okay, so let me solve this. 1 divided by 2.82. Okay, Neeraj, you can ask. Meanwhile, I will
Sir,
solve this.
from where did we get 0.026?
Basically, this KT, K into T, K is the elementary constant, and T is the value of the temperature, and over here temperature is 300 Kelvin. So if you multiply this elementary constant with the temperature,
Elementary meaning Boltzmann constant?
yes. Basically, whatever it is, for example, Planck's constant, electronic charge, Boltzmann constant, we say that these are elementary constants. Okay, fine. So it came out to be equal to for sorry my calculator. Okay, it came out to be equal to minus 35.3. 6. Okay, so if I multiply this 35.36 with this 0.026, it is coming out to be 0.919 minus 0.919 electron volts. Now let's check if any option is matching. What is the location of the Fermi level with respect to the conduction band? Yes, our option D is matching. 0.92 approximately. Yes, it is approximately 0.92 electron volts. So I guess this is enough for today's session. So if you have any queries except that blocks question that I will write step by step again, uh, we can end today's session so that you can join other session from my colleague. So if you have no question, you can leave the session. Thank you for attending. Thank you. Vinod, you can leave also if you have no question.